if I can see. Present to everyone. There we go. I'm presenting to everyone. And so we're on our two lesson optimization unit. And so today is just sort of, today's a little bit more about optimization and geometry. And then tomorrow is going to be specifically about economics.
Okay.
And so do you remember this? Did you ever do this one about the swimming area and you've got a certain amount of rope? And
yeah, that kind of question always didn't really make that much sense to me.
Oh, is that right?
Yeah.
Wow. How about
kind
that?
of the harder math questions.
Oh, okay. Well,
I don't know. I guess I was never, or I wasn't really paying attention in the earlier grades. I don't know.
It's kind of a neat problem because as you can imagine, like if you roped off this area and made a really, you could make a really long, skinny swimming area.
Yeah.
And beyond the fact that like that would be an impractical choice, like small children could drown at the end of this by the time you swim out and save them. There isn't very much area, or you could string it out this way and there wouldn't be very much area. Mind you, you'd probably be a lot safer. But anyways, the big idea behind most of these optimization problems is you're looking for some kind of a relationship that needs to be either minimized or maximized. And then often it involves two variables. And you're looking for a second relationship where you can relate the two variables together, substitute it into the original expression, and then get the whole thing in terms of one variable. And so I chose 240 meters here because it's some nice multiple of 12. And we're going to set this up. First of all, what's the thing that needs to be optimized?
Area.
Area, yes. And the good old formula for area is length times width. So look at that. I can't take the derivative of that. There's too many variables in there. So what we need to do is find a relationship between length and width. And of course, my perimeter is going to be the way in on that. So perimeter is equal to two of these widths and one of those lengths. And I know that my perimeter, is 240 meters. That might be kind of big. Two widths and one length. Now, here's the part where you kind of make a choice and then eventually you might regret it. It's hard to know sometimes which one is going to make the final expression easier. I'm going to go with, let's just have this as L, and it's 240 minus 2 times the width. I think that's going to make it easier because now I've got something I can substitute back into this expression in a really straightforward manner. So my area is equal to my length, which is actually 240 minus 2 times W. I'm going to put it in brackets, and then I'm going to multiply that by W. And so this is still length times width, but I've miraculously got it down to just one variable. I could use the product rule and take the, oh, sorry, hey, what should we do?
Whoa.
Pause the video and anyways, yeah, if you said take the derivative, that's right. So the question is, as we change the width, area is going to change. And so we'll take the derivative, and when we get to the point where our rate of change is 0, we'll know we've hit one of those extreme values. Okay, so the derivative of area with respect to width. Oh no, I want to simplify it first. Jeepers.
I was wondering.
I got too excited. I really wanted to use the product rule on it. Okay, minus 2W squared. This will be easier. There we go. Yeah, no, just too anxious to take the derivative. Okay, so 240, just using the power rule, minus 4w. And for a critical point, we are going to set the derivative equal to 0. You can see that, right?
Yep.
Okay, perfect. So 0 is equal to 240 minus 4w. Negative 240 is equal to negative 4w. And so w is equal to 240 divided by 4, which is going to be, what is this, 50 something? 50, 60? 50, 60? 60.
Yeah, 60.
That's right. Lindsay's grimacing and saying 60 because she's embarrassed on my behalf for not being able to do that. Okay, so it turns out that this is 60 and 60, and there's 240 meters of rope, and this is 120 along here. Okay, now technically, we could do the second derivative test just to make sure that this is a maximum and that we're not going to embarrassingly have discovered the smallest possible swimming area. And so if we took the second derivative, the second derivative is negative 4. And of course, it's negative. And so that means that it is concave down everywhere. Of course, it's a frowny face parabola, so we maybe knew that. So concave down for all w. So this thing is a maximum for sure. We know it for sure.
Okay.
Does that make sense?
Yeah, it makes perfect sense.
Yeah. So actually, a lot of interesting stuff gets done around optimization. In fact, Donald Trump, in his book, The Art of the Deal, talks about optimizing his buildings, which some people, yeah, it's like getting the absolute cheapest stuff that will work.
Of course.
Yeah. Well, it's legitimate. It's called it's called value engineering, and I'm sure it happens. You probably know it happens in construction all the time. You know, if one thing will do the job, you know, don't put an expensive one in.
No, exactly. Yeah.
Yeah. And in agriculture, it happens all the time. There are all kinds of optimums. So when I put nitrogen on canola, you know, if canola is a high price and nitrogen is a low price, I'm going to head for that optimum profit by punching up the nitrogen a bit. Okay. Next problem. And so this is a problem that involves Pythagorean theorem. So here's the story, everybody. It's not as compelling as some of the stories I've told. So I don't know. I used a natural gas pipeline. I actually didn't look up the price for natural gas pipeline underwater and above water. But this problem kind of works. And so we have a natural gas, I don't know, junction here on this side of the river. The river is 1 kilometer wide. And we want to pipe our natural gas down here to a power plant. And the power plant is 8 kilometers from the perpendicular distance across that river. Okay. The pipe that we put underwater, it's going to be a little bit more expensive. It's going to be $6 million per kilometer. I don't know. That's probably not enough money. And this is going to be $4 million per kilometer. I was going to bump those up to like 55 and 45, but even that's not realistic. Anytime you go in water, it costs you at least twice as much.
Wow.
So we're going to ignore the unrealistic nature of this problem, So as we pipe across the river, we could go straight across the river and then straight across the bank. But what we want to do maybe is take a little bit of a shortcut so that we can cut off our distance a little bit, and that might impact our cost just a bit. And so we're going to go over here to some point on the shoreline because we're cheapskates. We're going to cut off the distance. We're going to put our junction over here at some location X across the river. Fortunately, it's a nice arrow straight river. And so in order to find this pipeline length right there, what relationship can I use? It's right angle triangle.
The Pythagorean theorem.
Exactly, yes. So we can use the Pythagorean theorem to figure out this. I'm just going to put this at location X. And this is sort of what's going to define my relationship up here. But the thing that we're trying to optimize is the cost. Okay? So this hypotenuse is the square root of x squared plus 1. And it's going to cost us $6 million per kilometer to go across there. Okay. This full length here was 8 kilometers. And so I need an expression here for the distance that's left to travel. Anybody care to tell me what goes in brackets?
I don't know.
Lindsay's pointing at you. So this is 8, and this is x.
Oh, I see 8 minus x.
That is 8 minus x, yes. Okay. So
Okay.
a lot of these optimization problems that involve distance wind up being, you know, x and 8 minus x and things like that. Okay, so this is 8 minus x. And this is being sold for the bargain basement price of $4 million per kilometer. And so I'm just going to simplify this a little bit. 32 minus 4x. Okay. A cost function that only a mother could love. Nonetheless, we are going to bravely move forward and take the derivative. Not blindly because we're in calculus, but because we know we're looking for an optimum. Here we go. Okay, I've converted that to a 1/2, just because I think it'll make it easier. Okay, go over here. So the rate at which cost changes is I change my x. I can do this using the constant rule, and then I'm going to use the chain rule on this function. So the derivative of the outside, I just use the power rule. And I'm going to multiply it by the derivative of the inside. And I'm all done with this part. Whew. Okay, the derivative of 32 is nothing. Doesn't change. And the derivative of negative 4x is just negative 4. And so let's tidy the derivative up a little bit. 6 times 1/2 is 3, times 2x is 6x. And I'm going to use the third notation. Notice the use of the word third, which means like radical signs.
Okay.
I thought I'd throw it in there. For a critical point, what should we do? The answer is not take the derivative this time.
No, you want to set it to 0.
Yeah. Lindsay was making the 0 symbol in the air. Yes. So for a critical point, or critical points, we're going to take the derivative of the cost function. We're going to set it equal to 0. And you're going to see why I chose this particular cost function. It's because we wind up with this horrible square root. And the reason I chose this was so that we can see how to deal with these expressions that have square roots in them when we need to solve for x, or hopefully deal with them anyway. Any suggestions? You can hold out with me on this one if you like, because I'll break down right away and say what to do.
I'm not too sure.
Yeah. So the easiest way to deal with this situation, we're going to isolate the expression.
Oh, okay.
Yeah, that contains a square root. And then we're going to square both sides. And then that'll get rid of it. Okay.
Reminds me of physics when we were working with gamma, trying to solve for velocity.
Oh, right. Yeah.
And time dilation equations.
Good old time dilation equations.
Oh, yeah.
Yeah. So Einstein actually, as it turns out, he wasn't actually all that good at math.
No.
He worked with a lot of mathematicians on the mathematics around relativity. Mm-hmm. Okay, let's square both sides. 16 is equal to 36x squared. Whoa, that was close. X squared plus 1. Yeah, if you don't square that x, things go south in a hurry. Okay, and then we're going to multiply both sides by x squared plus 1. So it cancels over here. And we're going to expand the left-hand side. So 16x squared plus 16 is equal to 36x squared. Let's get the x's all on one side. 20x squared. And we're back over to the right-hand side of the board again. So 16 over 20 is equal to x squared. 4 over 5 equals x squared. X is equal to the square root of 4 over 5, which is 2 over the square root of 5. And if we really wanted to make it pretty, multiply top and bottom. Sorry, I'm going crazier than normal here. 2 root 5 over 5.
Yep.
Does it make sense?
Yeah, just where, okay, so at the beginning, where did you get root x squared plus 1?
Oh.
Like that part was a little, like, yeah. Where did that come from?
All right. So let's just head back to the...
Yeah, so you kind of have to redraw the...
I'll redraw the river. Is that like related to the sound, or is that just one of those? Okay. So the river, fortunately, was 1 kilometer wide. And we're going to cut off a corner with our pipeline. And we're headed over here. We're going X kilometers away from this perpendicular point right there. And so the actual distance of the pipeline across the river, this hypotenuse, is the square root of the squares of the other side. So that's where that came from. Does that make sense? Oh, see
Oops,
your,
I had my mic muted. Yeah. No, that makes sense. Yeah, that's good.
okay, yeah.
Yeah. So yeah. So then C will just okay.
Yeah. And we multiplied that by 6 because it's $6 million a kilometer. And we were left over, our leftover distance up here was 8 kilometers minus X. So we multiplied that one by 4.
Okay.
Then we just came up with our cost function.
That makes sense.
Yes. These are among the more difficult sort of optimization functions.
Oh, okay.
Yeah.
Good.
The ones with the Pythagorean theorem in them.
Okay.
Sort of, the secret is sometimes you'll have 2 radicals, sometimes you'll just have 1. But the secret is sort of to square things so you get rid of the radicals.
Okay.
And sometimes that doesn't work, but for most of these it does. So I haven't assigned all that many optimization problems. We've kind of got, we have 2 optimization lessons. I'm going to go ahead with, I'm actually going to start the next unit after this on Wednesday.
Yep.
We'll just do the lesson there because it's fairly easy. And I think there'll be an advantage for our next test. And then Thursday's review and Friday's curve sketching. So
Perfect.
yeah, I think Wednesday's the equinox. We're halfway through,
Oh, nice.
halfway through the course.
Good. Good.
Seems like we just got started.
Mm-hmm. No, it's been going well.
Yeah, happy. All right. Any other questions? Let me know.
I had a question actually about like what I emailed you about on Friday about the horizontal asymptotes.
Right. Okay.
So I think I've figured out kind of what doesn't make sense, and I've worked through that to make it make more sense. But I just kind of want to run my process by you and see if that works, because
sure,
it seems to work.
Yes.
Okay. So if I had a function like f at x is 2x squared, subtract 5x, subtract 3. Over x squared, subtract x, subtract 6.
Yes.
So I know that there's a horizontal asymptote at the point 2.
Yes. So
because you look at the degrees.
That's right. Same degree.
Yep.
All you have to do is look here and you'll see the 2. Yep.
So what I did to see which way the function approaches the asymptote is so as the limit as x approaches positive or negative infinity. So then I kind of just plugged in a really, really small value, or a really, really large negative value and a really large positive value.
Yes.
To the limit equation, and just solved the limit, and I got 2.07 for negative and 1.93 for positive, which would tell me that it's approaching it from the top or the bottom. Is that okay to do that way?
That is yes, that is totally okay.
Yep. Okay, because it just gives me a real like a sense of like when x is like negative 100, it's just coming down, or it's just coming, like it's right there.
Yes.
It's more practical.
Yes.
In my brain.
Yeah.
Okay.
No, and I do like that approach because it's like you say, like it makes it very real, right? If the number's bigger, it's from above. If it's smaller, it's from below. Mm-hmm. By and large, you know, there's only one place where it might fail, and it's probably never going to fail sort of in high school. Sometimes, because these are end behavior asymptotes,
Yeah.
We occasionally get these ones that, they do weird things, right?
Exactly.
Yeah, when they're close, they can actually,
Yep.
come up, cross the asymptote, and then approach it from above. But for all intents and purposes, your technique is going to work fine.
Okay.
And it's quite acceptable for high school.
Okay.
The other way, I think I was telling you,
Yeah.
if you do this division, you're going to end up with something like, 2 plus 1 over, I don't know, 2x plus 5. So for the sake of argument, when x is really big and negative, or when x is really big and negative, this expression is negative, and so you're going to be approaching 2 from below, because it's going to be 2 minus something. And when x is
okay.
And when x is
okay, I see.
yeah.
How would I do that division?
Beg your pardon?
How would I do that division?
You can just do it either by synthetic division or using the Bennett box. Like you can do synthetic or just whatever method works for you.
Okay.
Let's see. I could do it now, but I'd probably flummox it a little bit. Let's see. Oh. Can I do this? I can probably do it. Okay, Lindsay, how would I do this division if I had to use the Bennett box? Lindsay says, "Don't ask me. I don't know." Anyways, yeah, you can do the division any way you want to, and basically, yeah, you'll wind up with 2 over something.
Okay.
2 plus something over something.
Mm-hmm.
Anyways,
right.
So that's the other approach, but your way is fine.
Okay.
Yeah.
Yep, that was one of the questions, and then my other one was just about deriving difficult kind of rational functions and setting it to 0. Like if you had rational, like if you had a radical and figuring out the zeros for that, but we kind of just went over that now, so I'll take more look at that, but it's getting easier.
Yeah, what if you've got an example of that?
Yeah, let me see if I can. No, I don't think I have a specific one right here. I don't know where it went. But just like if we had a radical on the bottom of an expression and trying to figure out how to set it equal to 0 and solving for that.
Oh yeah, I can.
But, yeah, we did that here too. So that.
Yeah, so I can do that. And so if I had a horrible looking expression like that and I wanted to know what value of x made it 0, yeah, if it's in the denominator, you only have to worry about the top. So when when x plus 1 is 0, so when x is equal to -1, this expression will be equal to 0, as long as there's nothing weird happening like the bottom, like it's undefined at x equals -1.
Oh, I see. Okay.
Yep.
So would you would try to move the bottom term over to the other side by multiplying both sides by the term, and then it would just cancel out because you're multiplying by 0?
You could do that. Yeah.
Is that what happens, or yeah? I'm just.
Basically, what you're trying to do, like that, is actually a way that you can do it, and I would recommend, though, mostly just saying when the top is 0, this whole expression is equal to 0.
Yeah.
Right? So you're just headed for trying to find out where that happens.
Oh,
Zero.
okay, yeah.
Yeah.
I see.
So when x is -1, then it's going to be equal to 0. And, you know, it can get successively more complicated.
Mm-hmm.
So
Because now there would just be 2 x's, right?
now there's 2 values
Okay.
of x that are going to make the top equal to 0, and that's going to make the whole function equal to 0. Yeah, that's right.
All right, perfect.
Yeah.
Those are the only questions I got.
Okay, perfect. So your first technique is good. I like it. That's actually the way they seem to do it in the CEMC all the time. And then, yeah, just remember, it's just where the top is equal to 0. And might be trickier, you know, if you've got a radical and you're looking for those vertical asymptotes. But all right, perfect.
Alrighty.
So yeah, tomorrow's economics, it's really pretty easy. And then yeah. Okay. Thanks, Jeff.
Sounds good. Oh, yeah, thank you.
We'll see you.
Yep, see you tomorrow.